first hour and then see where it goes from there, depending on how far we get, is just give a statement of the dense model theorem and the uniform version, the what I'll call generation through adversarial boosting. Then look at different settings and applications, because I think these kind of reveal, these illustrate what the theorem is better than the statement of the theorem in many ways. And also it shows kind of the versatility of the general result, because so like I'll maybe like give some so like in crypto, in graph theory, in geometry, and in Fourier analysis, or like the four I was thinking we might talk about. Yes.
Just a quick question: is this, and I apologize to everybody else.
Yeah.
Is this written up someplace?
It's in the process of being written up someplace. So Tony has access to the so upon request, you can have access to it too.
So a preliminary version is not available in the archive.
There's nothing, no, but to people who actually want it, I will make it available. But it's preliminary, so I'll make it available in a format that changes every couple of days. In my Dropbox, yeah. So, but hopefully it's just going to improve and lengthen rather than get worse.
I think we could, Wesley, feel free to continue.
Okay. So, and then talk about how we get talk about maximum entropy, maximizing Shannon entropy using the reflective version. And then see what people want to talk about after. Hopefully, maybe do all that before the break, and then decide at the break where to continue, or decide at the break not to continue. One or the other. Okay. So the dense model theorem, at least the version I'm going to talk about, you have a distribution S on a set U. I'm going to use interchangeably the set U and an a priori distribution. Usually you think of as a uniform distribution on U. Okay. The only place where it's going to be important that it be the uniform distribution is when we're talking about maximum entropy, because then you want the uniform the a priori distribution to be the maximum possible entropy distribution. Okay, so and we're trying to find a model of S that respects a certain class of tests or hypotheses that I'm going to write as script H. So script H is a family of functions, or a class of functions, and for now I'm going to have H be, the range of H be minus 1 and 1. You can also, it's easy to extend it to make it the interval minus 1 to 1. But if they're unbounded, then you get into trouble. Okay. And then
Did you say that H is finite, a finite set of tests?
it doesn't have to be, actually. I mean, usually U is finite, and so H is finite. But, okay, that's really only because I'm allergic to integrals. If I just replaced all the sums with integrals, we could easily go to continuous spaces. Um, so I'm thinking of U as finite, and so hence H is finite, but everything I'm saying probably easily generalizes to the continuous case. I just have to change notation, which I don't like to do. Okay. And so we say that a distribution D, a distribution on U is epsilon indistinguishable for H from S if for every H in H the probability when X is chosen from D that H of X equals 1 minus the same probability when X is chosen from S is at most epsilon. So they have the only thing I'm going to assume about H is that the constant functions 1 and minus 1 are in H, and for now, if H is in H, then negative H is in H. And that's just going to that's just going to allow us to drop this absolute value without loss of generality. Okay. Okay. So otherwise, it can be pretty much anything. Okay. So. So capital G and little g are going to be specific functions that we use to combine elements, concepts in H, and in at least like the maybe I just say okay, I guess I don't need the sum for threshold. So in the main version, there are like different versions. So G is going to be just a threshold of see how many of them are 1, and if it's above a certain threshold, output 1, otherwise output minus 1. So you can think of it the sign of a linear combination of the HIs. And little g is going to be a real valued function. It's going to also depend on be symmetric, just depend on the sum of the HIs. We're going to have like this normalizing factor v that we subtract off, and then apply this function m that looks like this. For negative numbers less than 0, m of I equals e to the negative epsilon I if I is bigger than 0. Okay, so you have 1 up to 0, and then it starts dropping off, and you make epsilon relatively. The epsilon is going to be the same epsilon as here in order to prevent the drop off from being too steep.
So what are these? What I mean, I understand the formula,
Okay.
but what?
Well, how we're going to use these?
Yeah.
Okay, so okay. So we're going to have a kind of win-win argument saying either something good happens or something else good happens. Both are about understanding this distribution S. Okay, so saying there exists a k less than or equal to order, for every epsilon delta, there exists a k less than or equal to order log 1 over delta over epsilon squared. Okay, so you have some fixed constant times this, and the k is always at most that function. So that either so that there exists h1 through hk in H, so that either the function mu of x equals g of h1 of x through hk of x describes an epsilon indistinguishable distribution d sub mu to s. Okay, I should say so that for every s, there exists h1 through hk, so that either you get a model of this form with that little g, that particular little g, or for capital H equal capital G of h1 of x through hk of x. This is a witness that the distribution has a very small support. Oh, I should say describes a high min entropy distribution. Okay. So I'm going to make these terms a little bit more precise so that H is a witness that S has small min entropy. Okay, so to make this a little bit more precise, I'm going to I need to sort of define how a function describes a distribution. Okay, and second, how to characterize the min entropy of the distribution that you get from that function. Okay, and the third thing is what is a witness that the distribution has small min entropy. Okay, so let me first say, so the min entropy, so let's say like the relative min entropy of a distribution is the maximum of the probability the distribution assigns a point over the probability that the uniform distribution assigns that point. So usual the min okay, so I guess I should make it take a log to make it an entropy. Okay, so
Can I?
yes.
So with regard to the statement, so the little g in the statement of the definition of u of x is g of h1 through hk?
Right.
Down. That u of x is g of h1 through hk.
Right.
That's the same g as above, right?
That's right.
That specific g.
Saying there's actually kind of a family. So one choice, there's a number of results along these lines that you can prove, and one choice is to pick that particular g. And that's the one we're just going to use today.
Gotcha. And so the statement sort of is that you can find either
the
little h's, for which you get a good description of the distribution S, or that distribution is provably
is small.
concentrated.
That's right. So either you get a dense model, a distribution that's very flung out, that is indistinguishable from your distribution, that says the distribution looks dense, or you get this kind of area where the distribution looks sparse, and so you know that the distribution does not look dense. Okay. So the only kind of middle ground is it could look here. We say it looks sparse to some g of h1 through hk. Here it looks dense to just each individual hi. So here,
The word sparse, you mean
yeah,
sparse mean concentrated on
concentrated, right?
a few
Yeah.
things.
Right. And I realize this is kind of a not necessarily the most intuitive use of dense and sparse, but it was already called the dense model theorem when I came along. So I'm not fighting the tide on it. So
U is a probability distribution. It's just sort of not scaled properly.
yeah. So we just have to rescale it.
Okay.
Okay. So so remember, so G is in the range 1 to 0, 0 to 1. So well, we're going to think of this, so the induced distribution d of x is going to be renormalizing this. Okay. Saying using these as weights, but another way of thinking about this is as a rejection sampling procedure. So sample mu generates things according to this distribution. Say pick x at random, in the uniform way from u at random, with probability mu of x, output x, else repeat. Okay. So how long does this procedure take? The crucial thing that sort of like says how good this distribution is answers both how long does this procedure take on average, and what does it mean for the distribution to have high min entropy, is in this normalizing factor. Okay. So we call the density of mu is the expectation over x of mu of x. And the time that this procedure takes on average is, in expectation, 1 over the density of mu. Okay. But also, it's easy to check that the min entropy of this distribution D is at least, I should say, log of 1 over the density of u. Log because I made it in 2 bits by taking a log. Okay. So this tells us both the relative sparsity or density of D and how long this procedure takes. And they're the same answer. Or, one's a function of the other. Okay. So is this clear? Yeah.
And by how long it takes, you mean how long it takes to settle in on one of those decisions?
Well, so we're repeating if we don't like our answer.
Right.
So how many iterations on average we go through before we actually return a sample?
Gotcha.
So I'm assuming it's fairly easy to compute mu of x. So I'm not counting the time to compute mu of x. The only other thing and I'm not counting the time to draw the sample at random. But the main thing is the number of iterations we'll need to go through on average. It's like how many, each iteration we have a coin flip of whether we produce an answer is a coin flip of expectation exactly d of mu, and so the number of times we have to flip that coin before we come up heads is 1 in d mu. And it has a sharp tail if you go much longer than that. Okay, so so that's what I mean by this distribution d mu. Okay, the condition on high min entropy is going to be the condition, and d of mu is at least this parameter delta. Okay. And so the last thing I have to say is that what does it mean for something to be a witness that S has small min entropy? Okay.
Still low as an epsilon.
Yeah, and that's going to have the, well, no, the epsilon is here.
Oh, I see.
Maybe it's not here written nicely. So let me just, okay. But it's also going to be here. It's also coming in here. Okay. So,
So is it also robust in the sense that d is far from every high min entropy distribution, maybe in statistical distance?
yes. So,
Yeah, I mean, that is the strongest, in some sense, any notion would provide you that, right?
yeah. 'Cause, well, not any notion, but we want to make it robust so that things that are close together, it'll also be a witness for. So it's a witness that you're far from any high min entropy or low min entropy. I forget which way it's going. Okay. Okay. So so I'm going to use capital H to be like this function that's trying to be a witness that you're far from any distribution of low or high min entropy, I think is. So the so we'll say H is a delta epsilon prime. It's not, this one won't necessarily be the same epsilon as before. Witness of sparsity, or you can think of sparsity as really like maybe a better word would have been concentration, but that's not the word that's traditionally used. And this takes a little bit of getting used to. The probability when x is drawn from U that h of x equals 1 is less than or equal to, or strictly less than, I should make it, the probability when x is drawn from S that h of x equals 1 minus epsilon prime. Okay. So let me say it another way. If S were sort of a delta fraction of the whole universe, then we could lower bound this probability, okay, probability of any event, from saying, okay, well, let's look at the probability if we pick a random sample that it lands in S. And that would be this delta, because that would be sort of the fraction S is of the whole universe. Okay? And then times the conditional probability. So even if the probability is 0 outside of S, outside of the support of S, or then we'd have this as a lower bound for the, if S were really delta dense, then we'd have this as a lower bound for this probability. Okay. Now, if we had it, if we just put this, so saying, putting the inequality this way means this is really only possible if S is not delta dense. if S is more concentrated than that. Having this, but if we didn't have this epsilon prime here, then we'd get, and we allowed like any test, then we could look at tests that are vanishingly small probabilities, and you know, this is near zero and this is near zero, and even though in some sense that's a witness or a certificate that the density is small, that to verify that we would have to have so many samples that we'd be mapping out the whole distribution anyway, and then we could just look at its max entropy, min entropy, I should say. So by having this epsilon prime here, it means that not only is this a witness that is a proof that H is that S is relatively concentrated, it's a witness that's verifiable with about polynomial in 1 over epsilon prime samples to get a good estimate of both of these probabilities to within something like epsilon prime. Okay, so this means that you can think of epsilon prime as the kind of time parameter to check the certificate, and delta is what the certificate is proving. This makes sense? Okay. And if for some class H, S, if S has no delta epsilon prime witnesses of sparsity in H, we say S has delta epsilon prime pseudo density with respect to H. Okay. So having such a witness means you don't have pseudo density. Having pseudo density means you don't have such a witness.
So in this case, because of the epsilon prime, it's possible that you could be not delta sparse.
Yeah.
You could be not delta dense, but not have any witnesses.
That's right.
Okay.
And so let me give like a sort of canonical example of how you would get a something with pseudo density. In hindsight, so after we prove the dense model theorem, it'll turn out that this is like every example of pseudo density has this property. Okay, so okay, so say we've got a uniform distribution. You know, we might have a distribution that's small support, but looks like the uniform is indistinguishable from the uniform distribution. So we'll say that a distribution R is pseudo-random if R is epsilon indistinguishable from the uniform distribution or the a priori distribution.
Here, importantly, this notion of indistinguishable depends on your set H.
Yeah, and so I say pseudo-random with respect to H with respect to the same class H. So any non-trivial distribution is not going to be pseudo-random with respect to all tests, because you could like test the support, but it could be pseudo-random with respect to limited tests like polynomial time tests or tests expressible as low-degree polynomials, things like that. Okay. Okay. And so lots of constructions of pseudo-random tests look like. So now we could like home in on R and say, let's look at let S be like if S is delta dense in R, and R is epsilon pseudo-random, then S is delta epsilon pseudodense. Okay. So, and this is, I think this is right. It might be S is epsilon delta pseudodense, but
What is the meaning of delta density?
Yeah.
so delta is the amount. Oh, delta dense means that
Is it delta zero density?
is just that the this min entropy is at least log.
Oh,
In, but here we replace the U with R.
I see.
So or you can think of it as yeah. So the relative or if R is finite, you can just think of it as a fraction of R. You know, if R is a uniform distribution on a finite set, just pick any delta fraction. And then sort of like, if it's not, then look at convex versions of that, convex combinations of those things.
It's just a conditional measure.
Yeah. Yeah, so let's just say, so we can just say that this just means that S of X, the probability under S of X divided by the probability under R of X is at most 1 over delta.
So here, it's S is delta dense in R, but it may not be delta dense in D.
That's right. And it won't be delta dense in D because R is really sparse and S is a subset of R.
Okay, so that's why this is actually kind of a tricking effect.
That's right. So, yeah. So we'll see some examples, but I mean, yeah. So that's sort of the up to changing the, defining new hypotheses in terms of old ones. That's also like the universal explanation for when you're pseudodense. But it may not be immediately obvious that there is such a. We don't need to have explicitly defined what the pseudorandom set is. Okay. Okay. So okay. So now we have enough to actually define the last term in the statement here. Actually, so all I need to do is to say this H is a delta order epsilon delta or omega epsilon delta witness of sparsity for S. Okay. So let me just go through and kind of like translate again. So it's saying either there's a distribution, so for any distribution, either there's a distribution that's simply definable in terms of a small number of the same kind of tests that we're trying to fool, that looks like S as far as that class of tests is concerned, and has large density, okay, really large, is a delta fraction of the uniform distribution, or there's a succinctly describable reason why S doesn't look like any delta large fraction of the universe. Okay. Okay. Okay, and there's a uniform version of this that, or an algorithmic version of this that actually finds one or the other. Okay. It has to have a certain ingredient. You can't build it from nothing, so you need one ingredient. I'm going to just put it in the case when this ingredient is perfect. Often we're going to be using heuristics for this ingredient, and sometimes it works and sometimes it doesn't. Okay, but say a distinguisher, you give it S in some form, and mu, where the density of mu is at least delta. Okay. And if there exists an H in H, so that say H epsilon, some kind of C epsilon distinguishes d sum mu from S, then it returns an H prime in H that at least epsilon distinguishes. So it may not find the optimal distinguisher, but it's an approximation to finding the optimal distinguisher. Okay. And in particular, this means that if this fails to find the optimal, to find a good distinguisher, then really the distributions are C epsilon indistinguishable. Okay. This makes some constant, or I could even say epsilon 0, epsilon 1 is enough. See? So if you fail to find an epsilon 0 distinguishing test, that means there is no epsilon 1 distinguishing test. Okay. So if you have such a thing, then
You only need it for the entropy, right?
no.
You just have a.
How does the mu on the right side correspond to the mu in the middle? The same mu?
What this? Yeah. Well, so we're going to be running it on candidate mu's. So you write it, with, no mu, no h's at all. So like some fixed constant uniform distribution first. You get h1. You try that mu, and see if your distinguisher works. If it does, that defines h2, and you keep on going until your distinguisher fails, or until this function is a witness.
So this is like the weak learner in some sense.
This is the weak learner in boosting. And it's exactly the weak learner in boosting. We just plug it into the weak learner in boosting.
But it's better than the weak learner, right?
No, I'm saying this plays the role when you do the reduction.
But it's stronger, right? It's epsilon 1, epsilon 0. This is what I'm trying to clarify. Like, what is the difference?
No, this is the agnostic weak learner. This is the right definition of weak learner in an agnostic setting, I think.
Yeah. Saying if there's a way of predicting the function with correlation epsilon 0, you find one with correlation epsilon 1.
Yeah.
Or vice versa. I forget which one I called 0 and which one
I
1.
think in learning they define it as an approximation. So
Yeah.
if there is some weak learner that has opt correlation, then you
Yeah.
can find something with alpha times opt.
Right. Well, then I had the C, which would be
Yeah,
the
yeah.
alpha,
Yes.
but now I've yeah.
But I think it's precisely
Yeah. Yeah. So, okay. So, if we have access to a distinguisher, an epsilon 1, epsilon 0 distinguisher, then in k equals order log 1 over delta over epsilon 0 squared, we either find a h that is delta epsilon 0 delta witness, or a distribution d sub mu that is delta dense and epsilon 1 indistinguishable with respect to h. So the epsilon 0 influences the time and the quality of the witness. Epsilon 1 determines the quality of the indistinguishability, because epsilon 1 only matters if we get stuck. If we keep on continuing, then it's as if we were running the algorithm using the procedure with epsilon 0.
Yeah, except that you're also saying that this guy runs in some.
Well, so I'm saying this is how many I say calls to the distinguisher. So however long that takes, if the distinguisher is fast, that's as fast. If the distinguisher is slow, this is slow. If the distinguisher is non-constructive, this is non-constructive. Okay. So, but it just says everything except how you come up with this distinguisher is algorithmic. So once you have the distinguisher, then you're set. Okay. So how do we use I want to talk about it's like, well, how can we use this? So who here? I guess like at least half the people have like some complexity theory background, right? Okay, most people. So let me start with the complexity theory cryptography application, and I sort of came up with this in response to trying to like explain it to Shafi Goldwasser, but after I sort of vaguely remember a conversation with Evgeny Dodis that maybe he told me about it a long time ago, but I don't remember enough to give him credit or not. Okay. So I used R for pseudorandom before. I'm going to use the same R. It is going to be tied in with pseudorandomness, but not yet. Okay. So say that we've got like, in cryptography, this is a kind of a general situation. Randomness is cheap, but secret randomness is expensive. Randomness that you have to protect and not allow an attacker to learn, that's much more valuable. But like public randomness, that's not really an issue. If you don't care about the adversary learning it, you can flip a coin in public and everybody will know it. Okay. So say you've got a secret and it's been compromised to a small extent. You've got a secret R and it's been compromised to a small extent by the adversary. So in other words, the adversary has learned some L-bit message or L-bits of information about the secret. Call it L of R. So the only thing we're using about L of R is that the length is at most L. Okay, so intuitively we still have most of the randomness of R at our disposal, but we can't just use R directly as like a secret key that it may not be secure. Okay, so there's a very well-known kind of thing to do in this situation. And I'm hoping most people have heard of extractors. So an extractor is a function that you provide it some new randomness, and if you have a kind of compromised secret that's still mostly random, so if you have any distribution of relative max entropy or min entropy L, okay, then this is going to be some R prime, which is very close to the uniform distribution on something like n minus, you have to lose at least L bits, but you might lose a little more. And this is going to be true for almost all S's, even given S. A strong structure has this property even given the seed S, conditioned on the seed S. Okay, for most seeds S, if you pick it at random, then this using that fixed seed S, this is going to be close to the uniform distribution. Okay, but as I said, shared randomness is kind of expensive. So usually this is not how you didn't really pick R at random. What usually happens is you had a pseudorandom generator that maybe used a small seed, R, and stretched it into this big amount of randomness R. So you used a very small amount of randomness to determine your supposedly random secret. Okay. Well, what if you have a leakage now, whereas in this information theoretic argument, that leakage could really be about little r, because big R determines little r, or it could. So maybe you have like the leakage, same situation, but the leakage is about the little r. Now it's not clear that this construction should work. Okay, but it does, at least to some extent. There's some quantitative trade-off. Okay. Okay.
So L has to be clearly smaller than the seed length of the.
That's right. So the claim is, first, if R is epsilon indistinguishable, is epsilon pseudorandom versus, say, circuits of size S, then the distribution, let's say R, L of R, or L of little r, has 1 and 2 to the L pseudodensity, or 1 over L epsilon pseudodensity. Okay, and so we're losing something. The pseudodensity is exponentially small in L, and if you look at what we need to apply the dense model theorem, we're going to be essentially dividing this by this to get the epsilon, the final epsilon. So the final epsilon is going to increase by a 2 to the L factor. So that's going to prevent us from leaking all the bits about the seed.
So that means you can think of it as like however many bits long R is, you subtract L bits of information from that.
That's right.
You have that quality of the generator.
That's right. Exactly. Well, I mean, if the generator is sort of like perfect,
Yeah.
if the generator was not
Yeah,
maximally efficient, yeah,
I'm allergic to the constants.
right. Okay, so so we have to pay something with respect to L. Okay, so this is just a special case of the picture we drew. Okay, saying R. So here we're looking at first like the distribution RL, where L is randomly picked. that we're pseudo-random within that distribution, and now picking the actual L of R is picking a dense subset of that pseudorandom distribution. Okay, so okay, so then we can apply the dense model theorem. Okay, you know, with circuits of size S, if we were going to lose a little bit in the circuit size, about the factor of k, because we need to say apply this to a capital H, which is some composition of k things from. But it immediately follows that there exists a dense model D, a dense distribution D, so that D is indistinguishable from the distribution R, L of R, and so dense within, you know, uniformly chosen R and L. Okay, maybe I should make this R prime is like uniform version. Here R is the actual pseudorandom version. Okay, so and that these two are indistinguishable.
So what's R prime?
You know, we'll pay like we'll end up paying
With the extractor, right?
Oh, that one.
a factor of 2 to the L in the indistinguishability here.
Wait, is R prime the opposite of the extractor? I thought R prime is just uniform.
R prime is uniform. R is pseudorandom.
So you're saying you don't have. I'm confused. So you're saying you don't have.
So
You just have to know that there was an R prime that happened to come from the extractor. Is that what you're saying? That
oh, now I'm using R prime. Let me
Just use U.
let me use PRG. Okay. Let me just go back. If PRG, the distribution, apply the PRG to the R, then PRG of little r, L of R, has the pseudodensity. Okay. And then I can say that this means that D is a distribution of the form, you know, is dense within the distribution really random R, really random L. Okay. So and that's indistinguishable from the PRG at R and the real leakage function.
Here, this L is still like sampled from this like learning on some little R.
Right.
It's unrelated to the original little R.
Yeah, actually, what does L mean
Yeah.
for the uniform R?
What does L mean for the?
Yeah.
Oh, this is just independent L-bit string, random L-bit string.
But what if my learning function is just always 0 and this is false, right?
No, it's saying then the distribution is going to just plug in L equals 0. Because I'm saying it's dense within this distribution. So 1 and 2 to the L dense within this distribution. Plugging in all zeros is a special case. You know, so that's where the L happens to be 0 is 1 and 2 to the L fraction of all pairs RL.
I see. So in that case, it's like you learn nothing at the R.
Yeah.
I see.
The R is going to really be uniform. You know, otherwise it's going to be a giveaway. But
It's like a dense model, like in
Yeah.
some sense,
yeah.
it's a distribution that the PRT is going to pretend to.
So it doesn't guarantee that L is functional from R, but if it's not, you should be able to tell and use that to distinguish. Okay. So
So from what I understood, I think it's possible. Like the actual PRG pretends to be the uniform distribution. So in some sense, actual R is the dense model of the uniform distribution. And then this R is the replacement for the uniform distribution for which the new distribution is a dense model. Like
that is the same R as
No,
So
perhaps that's also.
so maybe I'll write, say D is going to be a distribution R sub D, L sub D. Okay, not necessarily independent. And this is going to be 1 and 2 to the L dense within random RL, uniform RL.
I know what L is, I just don't, not sure I understand what R means.
So,
R is the supposed output of the random.
Oh, that is what it is. Okay.
Yeah, so it's a random string of that same length.
That's what I thought, okay.
Okay, so
a uniformly random string.
uniform random string. R sub D is whatever, the same thing we're sampling from distribution D, and
Using notation, okay.
and we know that R sub D, L sub D is dense within RL. So essentially, R sub D, D has to assign each R sub D exactly one L sub D in order to meet the criteria. But
What's confusing is that you have R defined over there to be
Yeah, I think that is
PR,
scratched
G,
out.
little r. I think you should cross that out,
Yeah.
way to the left.
So,
wait, no, oh, okay. So I'm just saying,
Up at the top of the left.
yeah. So I'll just say I shouldn't say equals. If we replace
Yeah.
R with P sub G of little r, does the same argument work?
No, yeah, this is very natural, right? Like the actual R pretended to be actual uniform.
Yeah, but okay.
So
Yeah,
the R
but I
prime-
want to keep it for the uniform. Okay, so now,
So one question.
yeah,
The seed of the extractor
yeah.
is something that has to be known by the communicating party.
It can be, so we say like they just pick the seed and send it to each other in the clear, for example.
So this
So
we are assuming can be communicated without leakage.
no, with perfect leakage. The adversary knows it all because it's a strong extractor.
I see.
Okay, so we're saying S has to be random, but it doesn't have to be secret, and publicly known randomness is cheap. Okay. Okay. So and then we're essentially done, because if we use the extractor, we can like R prime sub D is the extractor from S on R sub D, and R prime sub D, even given L of L sub D, is going, R sub D is going to have high entropy, and so this is going to be approximately uniform for most S's. So this is going to look like a random string.
Now your definition of entropy is like the pseudo-density. It's
Um,
like a computational definition of entropy.
Well, now, so because this is just statistical distance, okay.
Right.
But now we say, well, okay, this model looked like what actually happened in the leakage world, and since this extractor is efficiently computable, if we could tell the difference between what we get by using the same construction with the pseudorandom generator, given in the presence of leakage, then we piece all the pieces together, and we could get an algorithm to break the pseudorandom
You need,
generator.
like S to be larger than the size of the extractor, or something like the size of the circuit size to be larger than the size of the extractor. Or something.
Yeah, so you lose an additive factor equal to the size of the extractor. You lose a multiplicative factor equal to this K.
So the S seed length on the extractor relative to the circuit size. Sorry, can you say it again? I missed that. And how that relates to K.
Okay, so
Yeah.
so we're saying, okay, if say in other words, the contrapositive is, say we've got a test that tells, I'm running out of board space, but okay. So if C, so we let like R prime pseudorandom generator be the extractor using randomness S of the pseudorandom generator, the pseudorandom sequence, then if we can if C1 distinguishes between R prime pseudorandom generator and truly random R prime, okay, then we'll get a C2 that distinguishes R prime pseudorandom generator from R prime sub D, okay, because R prime, when we use this D, that you know, we know it is uniform, okay, then that means we'll use that to get C3 of size roughly, you know, this is about the same size plus the time for the extractor. That distinguishes between the pairs R, D, LD and PRGR, L of R. And then we can use this to generate K different tests, you know, in our algorithm to generate K different tests. So there'll be a C4 that's order log 1 over delta over epsilon squared times the size of C3 that distinguishes, that breaks the original pseudorandom generator. Okay. So, but the main loss is that this will break the pseudorandom generator with distinguishing probability epsilon over 2 to the L if we have an epsilon distinguisher here. Okay, so we'll lose, we lose a factor of L here in the circuit size, but the main thing is that we lose a factor that's exponential in L in the distinguishing probability.
So is this the best possible? Could one ask the question of doing better in terms of the dependence on epsilon?
It seems like this is the best possible because if the pseudorandom generator were really exponentially secure, then if you could do better than this, you could leak the whole thing and still have some security left. Okay. Okay. Maybe this wasn't as clear. Okay, so I'm being a bit hand wavy here, but yeah. Okay, but let me just say one more word. Okay, so if we just had the dense model theorem, we could do all of this in a non-uniform model of complexity. By having the algorithmic version of the dense model theorem, it also holds in a uniform model of complexity. The only thing is, so you think of access to the adversary strategy. The adversary strategy is the leakage function L, and also at the end, the test for non-randomness. So if you have oracle access to the L and the test, then you can actually break the pseudorandom generator just using those as oracles with the amount of time, the overhead amount of time. Okay, so so after the break, I'll talk about some applications in combinatorics. Okay, sorry. So I might as well start. You're all sitting there. So, okay. So let's look at an application of the dense model theorem for graph cuts. And this was kind of implicitly done already, but actually by using the best version of dense model theorem, we can actually get quantitative improvement over what was known. Okay, so this is an example of sparse weak regularity. Sparse weak regularity is going on the heels of strong regularity from Zemaretti. Really, it should have been weak regularity first and then strong regularity, but actually the strong regularity was first, and then many years later, Fries and Canaan came up with a weak regularity that had much better parameters, and that only applied to dense graphs. So more recently, Koja, Aklin, and Fries came up with a version that applies for sparse graphs, but not if there's kind of a witness that they're sparse. Okay, so it has the same flavor as the dense model theorem, and in fact, you can view it as a special case of dense model theorem. And when you do it, you actually get an improvement in the results. Okay, so and I might have been forgetting another co-author on this paper, but if I am, I'm forgetting who it is. If you were a co-author on the paper, speak now.
Whatever hold your peace.
Yeah. Okay. So here we're thinking of we want to come up with an approximation to an individual graph. Where's the distribution? We think of the distribution as picking an edge of the graph at random, and that's a sub-distribution of the uniform distribution on all possible edges. And for simplicity, I'm going to make it a bipartite graph, where we have n nodes on one side and m nodes on the other. Because we want to look at tests that are cuts, and then we don't have to specify which endpoint is the A endpoint and which endpoint is the B endpoint, and what happens if they're both in the cut, if these two sets intersect. So we have a set of nodes on the left, a set of nodes on the right, and the function is 1 if the node on the left, from the left side, is in the first set, and the node on the right side is,
And the graph is fixed.
The graph is fixed, but we're thinking of it as a distribution on all the edges of the graph.
Of the edges of, and then you're putting a distribution on the edges that are in that graph.
Or we're thinking of the uniform distribution on the edges of that graph.
Of that graph.
And we're comparing that distribution to the uniform distribution on all the edges in the complete graph. Okay, and we want to say how different is it? Measure how different is it, or find some kind of high-level structure. And it says once we take care of this high-level structure, the rest of the graph looks kind of like a random graph. Okay, so let me say what a high-level structure is. So I sort of wrote it down here, but I'm sure I'm going to regret this. But so saying a high-level structure means that, maybe it isn't true that the graph, but the different parts of the graph look like they're picked with the same probability. But say we could break up the graph so that, except for the edge density, if we look at any two components, they look kind of like a random graph. So it's saying and so we can think of that if we're looking at the distribution of edges, it's going to be some distribution A1 up through AK, B1 up through BK. We can think of describing this random graph model as to pick a random edge from this model. We're fixing the number of edges in the graph, and then to say what a random edge looks like is saying for every pair, we have a probability distribution on which region the edge is coming from. So it's a probability distribution over pairs ij that tell you which region you're picking from. And then once we pick that, pick at random from that region. So I'll call this like a K partition distribution. See that? This is saying like the graph has this kind of very high level structure, but the details are random. This make sense?
The PIJs can be arbitrary?
The PIJs can be arbitrary. And, we'll get some restriction on them from the density, but for what we're interested in, I think it's mostly, we're not really interested in the restriction on the PIJs. And I'm not, often you get like restrictions on how uniform the partition is. I'm not going to care about those. Okay. So in this language, Kojo, Oglin, and Fries showed that if the graph has what they call the 1 in delta boundedness condition, and for some epsilon prime, and that says if you look at a cut that's not too small, the fraction of edges in that cut is about what is not a huge amount more than what it would be under the uniform distribution. So here's what it would be under the uniform distribution: A over n times B over m. You can say it's not more than a 1 in delta fraction more. Okay. Bring the delta over this side. This is the probability in the uniform distribution. This is the probability of an event in our set looking like the dense model theorem. And it is. But they put a condition on the, just like we did, they put a condition that says it doesn't this only applies when the A and the B are not infinitesimally small. So if there's some lower bound on how big you need the set to be, because like if you look at a particular edge, well, that edge is there in your graph with some probability. The probability under a random that it's there, that it's equal to a random edge is quite small. So if your graph is sparse, this isn't going to be true for very small sets. Okay. So then they say there's this there's a K partition distribution that's indistinguishable as far as cuts go. So, maybe to say that this distribution tells you the structure of your graph says if we look at any other kind of cut that's not, that intersects some fraction here and some fraction here, we can just look at the sizes of the intersections with the different pieces and use that to determine what to give an estimate of the probability of this cut, and that's going to be within epsilon of the actual value in our graph. Okay. Okay. So they give a so the key thing is that if you are 1 in delta bounded, they give a cut partition where K is exponential in negative epsilon squared times negative delta squared. Okay.
Is that big O or little o?
Sorry, this should be actually, no, this should be big O. So at most some constant times this. And I'm just hiding, the constant is just absolute. We're not like hiding any dependence on secret variables or the graph or anything like that. I just don't know whether it's like 2 or 4. Okay. Maybe like log base 2 of 3 or something. Okay. So let's just apply the dense model theorem. Okay. So you see that this condition actually is almost identical to saying this condition is almost identical to saying that under cuts. Oh, one thing I want to observe though, okay, is where are we getting these exponential functions? And they do this too. the reason why things are graded, there's really like a polynomial dependence, but it becomes an exponential dependence in the following way. Just like we had compositions of functions, they also look at compositions of cuts. And so we're both going to have to look at functions defined by little k cuts. Okay? Or distributions defined by little k cuts. And the observation is you know, any like Boolean function of little k cut functions can be, you know, the ones can be partitioned into something like 4 to the k bipartite graphs, complete bipartite graphs. Okay. And the reason is you just say, well, look at all the, you know, the a's that are used to define the left side of the cut, and just say, oh, well, let's look at any Boolean combination of these a's that defines a region in our partition. Do the same thing on the other side. So we now get 2 to the k, capital K is 2 to the little k, sets over here, capital K equals 2 to the little k, sets over here, and our function is just monotone on each complete bipartite graph. Okay. So you actually say partitioned into, instead of, yeah, into monochromatic complete bipartite graphs. So maybe I could even drop any function. So monochromatic means the function has the same value. Okay. Okay. So so if we've got this kind of pseudo density versus single cuts of size at least like an exponential, then we get pseudo density against any composition of function that's defined as composition of cuts, and in particular against that g of h1 through hk. Okay. So this condition with, and they had the epsilon prime being exponentially small, exactly the same condition implies pseudo density of the graph with respect to cuts. Okay, against the functions of cuts. Okay, which is exactly the condition that this h doesn't exist. Okay, therefore, applying the dense model theorem, we do get this measure mu that's defined in terms of little k cuts that's indistinguishable from it. And just applying the same partitioning process to mu, we get that the distribution on mu, if we, depends on only these little k cuts, means it's constant on every one of these complete bipartite graphs we get in the partitioning process. And that means it's exactly this kind of partition distribution. Because it's once we determine the groupings that things are in, that the two endpoints are in, every edge within that complete bipartite graph has the same probability, has the same weight, and hence the same probability, and so the conditional distribution is just uniform. Yes.
So in your dense theorem,
Yeah,
the
dense.
thing above,
Yeah.
it puts a bound on k that goes like log of 1 over delta.
That's right.
Divided by epsilon.
Exactly.
So if you kind of do this partitioning and counting thing,
Right. we get an improved value of k. Exactly. So we get the
Oh,
same.
okay, so
So we
that's
get the
what-
same thing, except that we can replace this k.
The delta goes on the outside. So
The delta. So we get something like 1 in delta to the order 1 in epsilon squared.
gotcha.
So instead of being, it's still exponential in epsilon, but instead of being exponential in delta, for fixed epsilon, it's just polynomial in delta. So we get the same thing, but with an improvement.
Is that tight?
I don't know if it's tight. Okay. But so just plugging into the dense model theorem, you don't have to do any additional work, and you get a better quantitative version.
Can you call this the sparse weak regularity?
Yeah. So it's sparse because it applies to sparse graphs.
Where is that used? Where is the assumption that
It's not an assumption that the graph is sparse. It's just that there is no assumption that the graph is dense.
Oh, I see.
Okay. So the previous weak regularity lemmas only worked when the graph was dense. Yeah. Okay.
And to go from the biologic to the general case.
Yeah, I mean, you just make copies of both sides,
Oh,
or you just view the graph as like having a directed edge in both directions. Same thing. So it makes it a little bit more convenient, because then you don't have to worry about like, oh, what if A and B intersect, and then both U is in A and V is in B. U and V are both in the intersection, and then you wanted to count that double. Oh, so one more thing that I should say is that they observed that there's an algorithm of Alona Naor, Asaf Naor, who's supposed to be here, that approximates the cut norm of a matrix. That's exactly what we need for our distinguisher to make this algorithmic. So you take the adjacency matrix for your graph, suitably normalized, you subtract off the sort of density matrix for your candidate distribution, you find the cut norm, you approximate the cut norm, and that gives you a cut that's approximately the optimal within a constant factor, like 4 times the growth in D constant of the, and so that is exactly the condition for the weak learner that we need. So plugging it into GAB, any result you get along these lines is totally algorithmic. You get a polynomial time algorithm in the size of the graph that computes this decomposition. I should say, okay, the decomposition takes exponential size in epsilon, polynomial in 1 over delta to describe. However, in both cases, there's kind of an implicit description that's logarithmic of that amount, right? So we get an implicit description of this partition graph in terms of, if we don't make the exponentially many, don't explicitly compute the partition, we still get a description of the distribution without spending that exponential amount of time. So, okay, so really it's kind of like, even though the output is exponential, the algorithm itself is like polynomial in all the parameters. Okay. Saying here's a case where we're explicitly computing the distribution, so we don't actually need the sampling procedure. So it's not, we can run it even when delta is incredibly small without worrying about it. Because we're explicitly computing all the probabilities of all the edges when we run the algorithm.
just because it's a small.
It's just because it's small. We're considering the universe as small rather than huge. Okay. So okay. So let me give like a similar application in Fourier analysis. of Boolean functions. Okay, so I'm going to use the exact same technique, but in a completely different domain. Oh, one thing I wanted to point out is we're using the dense model theorem here. And the whole point of the dense model theorem was to have a dense model. But we don't really care about that here. So we sort of shifted the point from giving us a dense model to giving us a simple model. And that's really all we cared about. So that's also going to be true, at least for part of what I'm going to show you in the next application. Okay. So
So can I
yeah.
When I say, so the strong one, what's the difference in the parameters?
Okay, the difference between like the Semiretti regularity lemma is that here we're saying that we're a good model against global cuts. Okay, the Semiretti is saying that even if you just look at most of these partitions, you can't find a distinguishing cut within that partition. So even if the partition is really small, you can't locally find a good a cut that sort of, you can't find a test that's built up of all these local tests that's a distinguisher. So,
What's the difference in the parameters then?
so then it becomes like a tower, and that's required. So we can come up with a strong regularity lemma by retrofitting, boosting, or retrofitting some of the proofs of regularity as boosting algorithms and come up with generalizations using this method. But
The tower
if the tower comes into it is
The height of the
It's
tower.
2 to the 2 to the 2 to the 1 over epsilon.
1 over epsilon time.
1 over epsilon times, yeah. And this is like proven to be
Okay.
necessary.
Okay, it's known that like a tower of, I think like it was known for a while that the tower had to be height like 1 in log epsilon, that you needed a tower and it depended on the height of the tower depended on epsilon. What was proved recently is like it has to be height at least like 1 in square root of epsilon or something like that. So it's still as towers go, a tower of height 1 over square root of epsilon is much different from a tower of height 1 over epsilon squared. But in some sense, you lose interest in exact constants because somehow, for some reason, I care more about the difference between 1 over epsilon and 1 over epsilon squared than I do between the difference between a tower of height 1 over epsilon and a tower of height 1 over epsilon squared. Okay. So, okay. So, let's say that S is we have like some Boolean function f over, let's say, gf2 to the n. So we're looking at all, the input is well, we're just looking at it's just a Boolean function, Boolean inputs, Boolean output, but I'm thinking of the inputs as being over gf2 to the n, so that we can look at like the for let's see what, say a subset of bit positions, we can look at okay. So these tell you the Fourier coefficients of this function. Okay. Okay. So and let alpha be the probability that f of x is 1. So a classic result using Chang's inequality, so I don't know whether it's due to, the proof is a corollary of Chang's inequality, but I don't know whether it was due to Chang or not, is that if you look at the set of A, so that so the normalized Fourier coefficient is like bigger than epsilon, so it's bigger than epsilon alpha. The span, so let's call this this set B sub epsilon. The span of B sub epsilon is at most the dimension. So all these big things fit into a small dimensional vector space. One over alpha over epsilon squared. Okay. So I'll prove this using the dense model theorem, but we'll also get a generalization. See? So the other case in the dense model theorem is going to be, okay.
What you wrote here, reviewing A is also an element in GF2, right?
You can.
What-
Yeah,
what-
so when we
how
talk about
define
span, right,
Yeah.
that's right, yeah.
Okay.
Yeah, that's a good point. Okay. Yeah, so these are also, subsets are also vectors in the same set. And we can generalize to like other fields as well. And the characters are also determined as field elements, and the same result is true. I'm just keep doing this for a little bit of simplicity.
So A is like a function rather than a vector.
No, A is a set of all elements.
A is a set of all coordinates or in the Fourier expansion that have,
B.
so B epsilon is the set of all A's.
So the epsilon is
Set of
the set
Fourier
of all large
equations.
Fourier equations.
Yeah.
Yes,
that have large weight.
indices of large Fourier equations.
Right.
So the span, I'm trying to, I mean, why isn't just the space spanned by the parity functions?
Well, many of the parity functions have small Fourier coefficient
Right,
for.
but isn't it just, aren't we just talking about the functions corresponding to the parity functions corresponding to the large?
Yes.
So it's just the number of them because they're all.
No.
But
'Cause they might-
They're not really independent over GF2 here.
Yeah.
Oh.
So like,
There is dependent between.
right.
That's the issue.
Yeah. So say that like F were the parity of some subset, then I think the ones with large Fourier coefficient are the ones going to be totally, whose support is totally contained in the complement of the subset. I think that's the kind of example where this is tight. So if you say, you know, F is the parity of all but log 1 over alpha of them, then the,
Like in some sense, it says that there is order of dependence in some sense, right?
Yeah.
They're saying that A and B are there, then A plus
Yeah.
B is also sort of quite likely to be included in this set of large coefficients.
Yeah, so that like the plot, S
Yeah.
plus X.
Yeah.
Small.
Yes, the sum set is.
okay.
So now I see what dense model.
Yeah. So, okay. So, we'll put a, so let's let little, so let's fix some delta and let little k be the same as before, log 1 over delta over epsilon squared. And we'll say that that S is, I guess, like delta. So F is delta pseudodense. I haven't just defined what the or delta 0 pseudodense if for every affine subspace of codimension k, so the dimension is going to be n minus k, and I need some notation for this. So what letter haven't I used?
Tau.
What, tau?
Are you going to use it for subspace?
Subspace, yeah.
You mean?
What?
Big V?
Phi? Okay. Okay. So the probability of f f of x equals 1, where x is picked from phi, is at most alpha over delta. Okay. So when you restrict to a big subspace, we're saying it doesn't totally blow up, go from alpha probability to alpha over delta probability. Okay. And that's going to be related to the pseudodensity of like the set of ones of the function. Okay. Okay. So what?
Just read that. I know what you mean.
Okay. So we'll say that F is delta 0 pseudodense. So just ignoring the epsilon, but just sort of hinting where, if for every affine subspace of codimension k, the probability of F when you look at an element drawn from that subspace, overall it's alpha. So if it hasn't gone up by a factor of 1 over delta. Okay. So the claim is if F is delta 0 pseudodense, then the dimension of the span of B epsilon is at most order log 1 over delta over epsilon squared. So you replace the alpha with the delta, otherwise get the same condition. And the first one follows from the second one, because if you put delta equal to alpha, then this is just saying the probability is at most 1, which is always true. So every function of bias alpha is alpha 0 pseudodense. Saying dense things are pseudodense. Okay. And so you recover the original from this. And once we've got it in this form, it's just a matter of plugging, this is getting very close to the dense model theorem. Okay. We let S be the uniform distribution on F inverse of 1. So look at our uniform input where F evaluates on the input to 1. Okay. We let H be the class of linear functions. Okay. And just like before, when for graphs, something that was a function of k things from H was constant on partitions. Here, a function of k linear functions is constant on the affine subspaces generated by those linear functions. Okay. So So anything of the form G of H1 through Hk is constant on the affine subspaces spanned by, or not spanned, but where, what affine subspaces that are shifts of the what, h of x equals 0, what's that called? Null space? Yeah. I think like there's a, this is making it too complicated, but just, h1 equals 0, h2 equals 0, that defines a subspace of codimension k, and you look at all affine shifts of that, and that's going to, each one, any function of this is going to be constant, because all the hi's are going to be constant. Okay, so that means that okay, and then saying that so we like break any such function down into affine subspaces where it's 1, and if in each one you haven't gone up by more than a factor of delta, then the same thing is true for the linear combination. And so that's exactly saying that your delta 0 pseudodense with respect to tests of this form. Okay, so S is, under the assumption, S is delta 0 pseudodense with respect to H, therefore has a model of density delta, but we don't really care about that. But there's a model d sub mu where mu is again some function of h1 through hk. And so mu on the same subspaces, same affine subspaces, mu is constant. Okay. And this is a model with respect to I should say also, it's easy to, again, just a calculation shows that b sub epsilon is exactly the set b sub epsilon over something like b sub 2 epsilon, wait a minute, one or the other, is exactly the set where the expectation of h when x is drawn from S is at least something like epsilon over 2. So the ones with large Fourier coefficients are just, and the alpha factor disappears in the normalization. So it's just those where the expectation under the set of ones is non-negotiable. Okay, and changes by some factor, constant factor. I forget whether it multiplies or divides. Okay, so these things. So the things we're trying to bound are those that have a large value. Having a large value, since this is really a model, an indistinguishable model from S, having a large value in S means having a large value in d sub mu. But anything that's not in the span of h1 through hk, any linear function that's in the span of h1 through hk, has 0 expectation in d mu in any of these affine subspaces. Okay. And taking the parity of something not in there just disappears. So that means anything that's not in the span of these k things, it has expectation 0 in d sub mu, which means very small expectation in s sub mu, means it's not in b sub epsilon. So we've given an explicit. This also gives a explicit vector space of codimension k that that contains all the large Fourier coefficients. And again, even though the whole point of the dense model theorem was density, here we're not using density. Just that
They're
is,
quite related in some sense.
yeah, simplicity and density, you know, yeah, but it's somewhat ironic that we're throw away what was the headline in some of the versions. Okay, so okay. Oh, one other thing I wanted to say in this setting is that I say explicit, but this is a setting where you can in some sense provably not have an algorithmic version, where not only is there no distinguisher, there isn't going to be an algorithm that, given samples from a distribution with pseudodensity, actually finds you the model. And under the assumption that learning parity with noise is difficult. And if you're familiar with the learning parity with noise, it's essentially saying, hey, you can't distinguish between things, distributions where there is a bias of some linear test and the uniform distribution. So it's not surprising that under that assumption, you can't do much algorithmically in this context. So, so we don't always get an algorithmic version. Okay, and so I guess I was going to show the high entropy stuff, but I guess I'll have to do that at a volunteer basis because I'm keeping people from lunch. So I'll stop here.